So everyone, welcome to BayPiggies. So we're going to have two talks tonight. One is going to be a short talk by myself, and the other is a longer talk by Bill Deegan. The kind of theme of the evening is build systems. So we'll see two of them that have been written in Python. And I should, Bill is one of our co-organizers. He's the guy behind the website, and he does a lot of other cool stuff. And Bill is big expert in DevOps and build systems and things like that. So, and one of the developers of SCons. So that should be a very interesting talk. And mine is about Snakemake, so you'll find out about that in a minute. Okay, I'm going to talk about Snakemake, which is an automation tool for reproducible data pipelines. So a little bit about what Snakemake is. I was actually looking for examples of bioinformatics pipelines for another project of mine, which is data workspaces. I gave a talk on that last year. And in the process, I came across this tool, Snakemake, and most of the bioinformatics workflow tools seem to be all written in Java. And I'm not a big fan of heavyweight Java systems. And so I saw this one, it's written in Python, and it actually seems to be fairly widely used. And pretty interesting. So, so this is sort of my experience using it over the last couple months. So it's a workflow system for bioinformatics. It could be used for other things as well. It's not, it's not strictly for bioinformatics. But there is a few special features for that and for data science type of things. And you can think of it as if say SCons is a build system for code, or Make, which I know more about, is a build system for code, then Snakemake is really a build system for data. And we'll kind of see what that means in the examples. So it was created by Johannes Koster in 2012. I think he did it as a part of his PhD, and now he's a professor in Germany working on algorithms for reproducible bioinformatics. So I think this seems to be very actively developed by him and his team. You can use it to define your workflow as rules using Python and a domain-specific language, kind of intermixed, as we'll see in some examples. Each rule is really defining kind of, you basically have a step in your workflow, and you define what is the action you're going to take, and that could be some shell code like you would do in a Makefile, or it could be inline Python, or you can call a Jupyter notebook, any of those kinds of things. And then you define what are your input files explicitly and what are your output files. And so it's a little more explicit than Make, because it doesn't know as much about kind of the individual steps, but it can use that information and build a dependency graph for you. And with that dependency graph, then it can use it to basically only build the stuff that you need to build. So if you change some data, kind of partway through, you don't have to run the beginning part of your pipeline. It's for also, it can parallelize things automatically. So it looks at the build graph and can figure out, what can be run in parallel without you having to do anything special. It has a lot of cool features, including integrations with Python, of course, as I mentioned, with Jupyter notebooks, with Conda. So each step can actually be a separate Conda environment if you want that. Like I mentioned, it supports parallelism. And I haven't used this, but it has features like if you want to run this on Google Cloud or Azure or Kubernetes or various kind of high performance computing clusters, you can do that as well. So I think it really scales from, say, your laptop to the cloud. Okay. So I'm going to walk through a example scenario to kind of motivate this and show you kind of what some of the rules look like in the actual syntax. So this is a climate analysis using ocean buoy data. And the idea is that you can download this data from the US government, and it's sensor readings like every hour. And in some cases, it goes back like 50 years. And so there's sort of kind of two steps in the analysis. The first is there's a bunch of these files that we've downloaded. And we have, like, for each buoy, for each year. We have one file. And so they're kind of organized in directories. So each buoy has a number. And so these are all the files for that particular buoy, one per year. And so there's a first step is this preprocessed.py. And what it's doing is reading the files for a buoy, kind of cleaning them up because there's things like, 2-digit versus 4-digit dates and weird ways of indicating missing data and things like that. So it cleans it all up and creates a big data frame for that buoy and then saves it to a file as a compressed CSV file. So that's the first phase. And then in the second phase, it's running a Jupyter notebook, and there's one of these per buoy. And that's reading that data in and doing the actual statistical analysis and producing some pretty pictures. And so there's four graphs that get generated for each buoy. And it's basically 2 different readings and 2 different formats. So this is kind of what it looks like. And currently there's like only 4 buoys in the thing, but you could kind of imagine you want to do this across maybe, there's maybe 1,000 buoys total, but that's a lot of downloading. Anyway, so this is what we want to automate. So I'm going to go through step by step. So this is kind of what the first rule looks like for the pre-process step. And this goes into, so like you remember there in Make, you have this file called Makefile. So they have one called Snakefile, and that's where where you put all these rules. And so in case the rule you have, this is using their kind of domain specific language. So you say rule and you say pre-process, and then each rule has some inputs, some outputs, and then some action. And so here you can have a list of inputs or outputs, and these could be explicitly enumerating files, or you can use wildcards. And the wildcards kind of are pretty powerful because I can say, okay, there's a directory that has the number of the buoy, that has all the files in it, so that's the input. Then the output is going to be a process file with the same buoy number in it. And then when I want to run the shell script, I'm going to pass that buoy number as a parameter to that script. So rather than having, say, 1 per buoy, 1 rule per buoy, I can just have 1 rule and use the wildcards. So that's kind of pretty powerful. And unlike kind of say a traditional Make, you do have to kind of explicitly list your dependencies and things. But as you can see here, then once it has that information, it can use that in its dependency graph. So here's the second step. And so this is kind of run a Jupyter notebook. And this rule is called anomaly analysis. And it's also using the wildcards. And so you see we have the output from the previous step is the input for this step. And then we're going to generate these 4 output files based on that wildcard. Now, by using this notebook action, then I'm saying I'm going to run this particular notebook. And the notebook is also kind of parameterized by the wildcard, so it'll run a different notebook for each buoy. And this log thing, what this is for is when it runs a notebook, it's, one of the things kind of when you run a Jupyter notebook is it's kind of modifying the notebook itself. And so this is more like treating the notebook like source code. So what it'll do is it'll make a copy of the notebook and then run that copy. So this version of the notebook is read-only, and this log here is kind of where the actual evaluated notebook will show up. So if you wanted to kind of review what that was, that could also be like an output for this step as well. One thing I should mention is that, so you see I have like a separate notebook for each buoy. That's because the project was organized that way. But you can actually, I could have actually passed this as a parameter into the notebook, and I only had 1 notebook. Anyway, so that's what the second step looks like. And then at the end, you need what's called a target rule. And the idea here is if you're using wildcards, it needs to know kind of, you can't kind of use that as your ultimate target because it needs to know which files exactly you want to instantiate. So what I'm going to do is define a rule all, and I'll say its input is the files that I want, which these are the output files. And then I can just, this is just Python code right here. So you can intermix Python code. You can have functions, whatever you want in your make file. So here I'm just listing, these are the buoy names that I want to generate. Then this rule is going to kind of use this. And this expand is just a function that's going to expand it for each buoy that we have in the list, as well as each of the 2 formats. And so then if you put this as the first rule in the file, then it will run this rule by default. And anyway, so that's the target rule. Now, when you want to run the workflow, you just say Snakemake and -- cores, and you can tell it how much parallelism you want, and so like you could use 1 as the standard, and it will use the snake file you have in the current directory to define the rules. And so it's going to pick the first rule, which in this case is all, and run all those. Now you can parallelize this by, like, if you put 4, so I kind of compared on my laptop. So this is a MacBook Pro, not the newest, it's like maybe 2017 vintage. So if I run it, it's like 1:50. If I run with 4 cores, it's 53 seconds. So it does speed up the build, so I use the parallelism. And I'm assuming that these people doing the big scientific workflows have like 60 cores or something like that. So for them, it's a big deal. So if you want to do a cleanup, if you want to clean up everything, you can say Snakemake and put this -- delete all output, and it'll figure out what are all the output files that would be generated and make sure they're all deleted. So, and not delete the inputs, obviously. So a little bit about my experiences personally with Snakemake. So good things are, it has a powerful automation. So you can see that I automated that workflow with, just, I don't know, maybe 25 lines of code or even less. And you can always drop them on. So if there's something that's more complicated than kind of what their rule-based model can do, you can use Python there. You don't have to think too much about what needs to be rerun because it knows about your dependencies. So like in the project that I was doing, and this thing here is a graph of that, it was fairly complicated. You can see like there's some stuff where I'm actually building a graph database, running queries from it. I'm running Jupyter notebooks. I'm running the Python imaging library. I'm doing all kinds of things that generate basically a website. And so what I can do is if I'm mucked with something in the middle, I can kind of just go in and just rerun it, and it'll know what's changed and then regenerate the output. And I can, some of the stuff at the beginning is expensive, so I don't have to rerun from the beginning. So the other thing, obviously, the integrations with Jupyter and all are really convenient and a little nicer than kind of using some of those, I don't know, NB run or whatever the thing is to run it from the command line. So not so good things. So wildcard rules can get a little tricky to get right. So, it took me a few tries on some of the wildcard rules to get what I wanted. And, so you kind of go through the documentation, think about it, and try something. If it gives you an error, then you tweak it a little bit. So it's not the simplest thing in the world, the wildcard rules, although always the fallback is to be explicit about what files you have. And if you have an existing project, you might have to restructure it a little bit. For the one I just showed you, I didn't do any restructuring, but my bigger one over here, I had to restructure a few minor things. And one thing I would just mention, this is my nitpick, is that the command line is a little awkward because like I had to put this -- cores equals 1 every time. I like to have really short commands. But I'm guessing that, they if you have tons and tons of cores, they want to make that convenient. But anyway, that's just my nitpick. So if you want some more information, this is their main website, and I'm going to copy all these links, or at least the link to my slides and the link to the Snakemake site into the chat on the meeting, so you can have that in just a minute. And they have a tutorial. There's a poster there, and this is my presentation if you want to look at that. So does anyone have any questions? I see.
Actually, there are two. Do
Okay.
you want to read them?
Or can you read them? When I click on it, I'm not getting anything.
What, if anything, is Snakemake missing to be used as a build system for code?
Well, I would say what it's kind of missing, if I compare it to, say, like Make and maybe SCons, I don't know anything about it. I will in like 30 minutes, I'll be an expert. But I think it's missing kind of, it doesn't know anything about any of the individual steps, because it's assuming if you have like a data pipeline, each step is very ad hoc. So you have to kind of do a little more work. Whereas if you know it's a C compiler, and that if it has these options, it's going to go from a .o to you know, an executable from a C, .c to a .o, that kind of stuff. So it's kind of missing that kind of built-in knowledge. Obviously, it also makes it a little cleaner, but you could use it to build code, but I'm guessing there's better tools for that. So
Next question. Why do you think 4 cores was only twice as fast as the 1 core? The clock rate isn't twice as fast when using only 1 core. Why is it not able to parallelize most of it?
well, I would
It might
imagine
even be a, go ahead.
yeah, I was going to guess that it's two things. One is you're also doing IO. So depending on what the you know, I mean, it has a SSD in there, so it should be fast, but it may be limited by that. There's going to be some steps, you know, I guess theory it should, since there's 4 buoys, that they should all be running in parallel. But, you know, we'd have to look at that. And the other thing is, you know, that's, you know, I think that's 4 cores. That's kind of Intel threads, so they're not real cores. So, you know, I think you only get like 20% for the extra thread.
And Dave Beasley gave a really good talk on something like that at a PyCon about 10 years ago, which you really showed that sometimes the more you gave it, the slower it got. Super interesting as well.
Cool.
That's all the questions we have here. There is an announcement though, Jeff. Do you want me to read that as well?
Sure.
So it looks like, oops, I just lost the announcement because I Jeff changed his screening. 1 second.
As he gets that, Jeff, just as you think a lot about data, what are your thoughts on Snakemake versus Cromwell?
Cromwell.
Or if you looked at it, it's an alternate Cromwell and a workflow language.
I'm not sure because I looked at a few. Is that one of the Java-based ones?
I feel like I should know that answer.
Okay. Yeah, well, so I haven't looked at all. I just saw some that were kind of very heavyweight, and there's like this common workflow language definition and stuff. And I would say one thing about Snakemake, well, I'm assuming that those things, some of those may have a GUI and stuff. So if you like to draw boxes and arrows.
No, I think that similarly you're constructing. It's okay if you haven't looked at it all. Sometimes you've got more knowledge, and just because you gave a talk on this, it's an alternate workflow pipeline kind of language, giving kind of like a YAML kind of experience to get data pipelines.
Oh, okay. Well, I'll look at that one then.
Yeah, I think it's.
There is one more question I see. So the question, which I actually meant to mention in the talk but forgot, is how does it determine what's going to be rebuilt is actually this timestamps. So.
And we also have an announcement. Jeff, do you remember Al Swigert?
Yeah.
He actually came and spoke for us several times. It looks like he actually has another book out. So everyone knows he's the one who wrote Automate the Boring Stuff with Python. And his new book from No Starch Press is called Beyond the Basic Stuff. Yeah, I want to make sure I didn't reread the boring and the basic. So he has something a bit more advanced. It looks like it's coming out, or it's actually just came out. So cool.
Cool. Yeah, all his books are really cool.
Yeah, it's a great way of breaking things down and making it clear too.
Okay.
Karen, have you made Karen?
Anything else before we move to the main?
I'm sorry, what was that?
Hey, Karen, I think Bill might need to be able to do some screen sharing. You might need a little bit of your help. And Jeff, it looks like there was a question that came in, not through the Q&A, but through chat. Does your laptop have 2 cores with hyper-threading?
I think that's what it is. I'd have to go. I have like 3 Macs because I'm a consultant, so I have multiple clients. And so remembering what each one has, let's see, I can tell you now.
Bill, you're a co-host now. I set Glenn and Jeff up a little bit earlier. You joined a little bit later. You're a co-host now. You should have the freedom to do video and also share content.
Oh, I have actually, this is actually a dual core Intel Core i7. So getting that speed up is pretty good actually.
So I put a little initial slide with a bunch of websites and ways you can contact the project and contact me and download the project, etc. And the documentation for SCons is pretty extensive. The user's guide is about 200 plus pages, and the man page is probably 50, 60 pages, something like that. So let's start out with a little bit of history. SCons was written initially in 2000 as part of a competition from the software carpentry build competition written by Stephen Knight. It was a reimplementation of a Perl-based make system called Cons, but carried over a lot of the concepts. It's multi-platform, so you can build pretty much every platform known to man. It's fairly actively developed. We have a Discord server, an IRC channel, a user's mailing list if you need to contact us. We get about 40, 50,000 downloads a month. And it's used pretty broadly in production for commercial products. MongoDB is very active in the community, is a name people might recognize. VMware also uses it. Godot, which is a game framework. And a lot of embedded software, a lot of basically complicated builds end up using it because while you can use it for simple builds, it makes those pretty much trivial. Complicated builds, it makes them like repeatable and workable. So SCons is up on PyPy, so if you wanted to install it, you just need to make sure you have Python 3.5 or higher, and just do pip install and you'll have it. The makefile equivalents for SCons are called sconstructs or scon scripts. They're plain Python, and they basically call APIs, which are in the man page, to specify what it is you want to build. Now, looking at Jeff's example, you could probably implement that entire thing in SCons pretty trivially. Where he had rules, SCons implements that concept as a builder, and it has a lot of powerful features, which we're not going to go into tonight because literally you could talk for hours about all the features and things that SCons can do. The goal is sort of give you a basic taste of SCons, a little bit of the syntax, and a little bit of details on some of the core concepts. So let's take a look. So this is pretty much your simplest example. If you wanted to build a program, you just say program main.c and you run it. And that would produce your executable on pretty much any platform as long as you have an installed compiler. SCons will detect and configure a vast assortment of compilers, MSVC, MingW, GCC, Apple compilers, CLang, et cetera, et cetera. That's part of the batteries included. If you had some unusual compiler, if you're cross-compiling, you can set up those tools for use by SCons, depending on how unusual it is, pretty trivially. Okay, so let's talk about what a builder is. A builder is a basic functionality we use to describe how to produce a target from a source. The simplest thing, this might be just saying, hey, we're going to call it GCC, we're going to tell it to output at the target, and then list the sources. But you can specify the command line using variables. And I don't know how familiar people are with makefiles, but typically in make, you would specify some wildcard rules, and those would use strings that expand into the command line. So it would have include pass, it would have preprocessor defines, it would have all the different things in the command line which expand out with sort of variable string expansion. For many builders or most builders, you don't have to specify the output file, it would figure them out. So In the case of program main.c, it's going to know, okay, I've got a C file. I need to produce an object file. And from that, I need to produce an executable file. So we'll add the intermediate file of the .o, and then it will use that as the source for the executable. And I have some output from running SCons a bit later on. There's a pretty large collection of included builders for not just for software, but for things like building documentation. There are user contributed builders for doing many things, and pretty much any process flow you want to automate, you could do with SCons. And just a quick list of these programming languages that have built-in support. All right. So when in our example here, we are calling program main.c. Now, SCons has the concept of a default environment, and that's a construction environment. Now, a construction environment basically holds all the information about the environment you want to configure to build your software. So any preprocessor defines, any compiler flags you want to add, any library paths you want to add, all that type of thing. Any unusual tools you wanted to add, you set those all up through your environment, and then those could be used by the builders attached to that environment. And we'll do a little, there's an example a little bit later. But to create an environment, you just say env environment, and this is just plain Python. So the variable name can be whatever you want. And environment will set up tons of information for you. And then you can also add things called variables for handling additional command lines to your build. So you might do things like SCons build type equals release, build type equals debug, platform equals 32-bit, things like that. Okay, let's do a little more complicated example. We're going to build a shared library, and we're going to link it into a program. So here's the S construct you would use for doing that. So first you create a environment, and in this case we're saying the lib path to be the current directory. Then you just say, hey, build me a shared library. Here's the library name. Now notice it's XYZ. Oops. And it's not libxyz.so, it's not xyz.dll. It's just the library name. SCons will construct an appropriate file name given that. And then you can just list the sources you want it to include in the shared library, and it will build a tree of what needs to be done. And there's some examples later that will show you more detail of that. And then the program, you just say the target. So you give it a program name, the source. And in this case, we're linking the lib XYZ. And were you to run SCons, here's what you'll see. So first it's going to compile the application's object file, build the library source file, build the shared library, and then link it. And oh, I forgot to mention, well, there's a little step-by-step here. So one key concept that does confuse people about SCons, and it's pretty basic. When SCons processes your S construct, nothing gets built. All you're doing is instructing SCons what it is that you want to be built, and nothing gets built until all the S constructs and SCon scripts are processed. So in this case, you see it saying reading SCon script files, done reading SCon script files, and then it starts building the targets. So only certain things can happen in those SCons script files. And everything else has to happen afterwards. So when you're building complicated builders that need access to files that are created after the build starts, or may not be there after the build starts, you just have to keep these things in your mind when you're doing it, because otherwise you won't understand why things aren't working for you. Okay. Now, as I said before, builders will create their command lines. And one thing that makes SCons fairly unique, although since SCons was initially released, a lot of other build systems have also started doing this. When SCons determines whether a target is out of date, it will also consider the command line used to compile it. So if you change a preprocessor flag, if you change an include path, that will instruct SCons that it needs to be rebuilt, even though you may not have touched any source files. Now, not everything on your command line will you want, or may you want, to cause a recompile. And you can wrap those things that you do not want to cause a recompile with this $parens and $close parens. So I have a little slide on exactly what that does. Now, as I said before, SCons will look at the command line to determine if things are out of date, but it can also determine, use various methods to determine whether the target files are out of date with respect to the source files. And these are configurable. SCons has a concept called a decider, and there are at least 3 built-in deciders, with the default being the MD5 decider, which will take an MD5 hash of the sources and compare it with the MD5 hash of the sources the last time you built whatever target that was. If it's changed, it'll rebuild. So the timestamp in that case would be ignored. It only cares if the contents has changed. MD5 timestamp will use the timestamp and only check the MD5 of the files if the timestamp has changed. MD5ing a file is obviously not as fast as just checking timestamp. So this is a way to speed up the build a little bit. Or you can go with the make, or I guess Snakemake type of decision process, where you just check and see if the timestamp is newer than the previous build or newer than the target. And SCons allows you to create your own custom deciders. So for example, if your sources all resided in a remote Git repo, you could actually get fetch over the network the current hash from the Git repo and use that to decide if your sources have changed and if your things need to be rebuilt. Or that you could do any number of things to use to decide whether targets are out of date with sources. As I said, we could probably talk for hours about the many features and functions that SCons would allow you to implement your build system with. All right, so some common things that you want to do when you're building software. The first one is you want to not pollute your source directories with the targets, with your objects, with your programs. You want your source directories to only be your sources. And this also makes it much simpler to make sure you have a clean build, because nothing ever gets written in your source directories, and you could just completely remove the build tree. Additionally, you may want to build several flavors. I've seen this where the same source code would be used to build 32 and 64-bit, debug and release, and profile all at the same time. So you could have 6 possible builds happening all at the same time. or individually select them. They can build in parallel. So rather than having to do something like CMake, release, flags, generate makefile or a Ninja file and run that, then change the flags and run it again, you just say SCons build, and it would build them all potentially at the same time. Also, you could do this for embedded, where you might have 99 different boards you're building for that all need a different compiler tree. You could build them all at the same time, and they'll intermesh in parallel. So in this case, we're going to use, and that concept is called a variant dir. So the idea is you might have multiple variants that you're building from the same sources. And this is a fairly simple example of how to use a variant dir. So in this case, we've created an environment, and we'll set the preprocessor path. We'll set a set of C preprocessor defines, and we will build the sources under the source directory into a target variant dir of build vanilla. Then we'll create a clone of that environment and change only the flavor to chocolate, and then we'll build that into build chocolate. And so you end up with a top-level S construct, which references a lower-level S conscript, and that's used to build the variants. So this is the first-level S conscript, which is going to build a library and an app. These are the S conscripts for the app and the library. So the app is just going to build a program using the library, and the library is just going to build a static library in this build. All right, so if we run SCons, we can see it build all of that. We build all of chocolate and all of vanilla with differing flags. You can see for chocolate, you can see flavors defined as chocolate, and for vanilla, and you'll notice the order just isn't tied to the order that things are listed in the S construct. So in this case, we specify vanilla first and then chocolate. And it actually built chocolate and then vanilla. So you're never specifying order to SCons. You're specifying dependencies. And that's another key concept that a lot of people get hung up on when they first try and use SCons. Coming from Make, coming from a lot of other build systems where specifying order is the norm, but honestly, it's not the correct thing to do. The correct thing is always to specify this target comes from this source, this target comes from this source. Specifying by order is actually kind of cheating, and if you miss an order because you don't fully understand everything that's happening in your build, you could end up with a build that doesn't properly build incrementally. And then you can literally waste hours and days wondering why your build doesn't work properly, or why some change didn't propagate to one of your libraries. And then when things linked, everything broke, you get memory crashes. So this is one of the problems that SCons aims to remove, reduce, minimize, make it easier to figure out what's going on. All right. So SCons has built in a lot of tools to help you figure out, why is my build not working? Why are things being rebuilt? In this case, you can look at the dependency tree, which SCons generates from the specified program and static library. You can see, in this case, I'm only showing the build chocolate app. So you can see the graphically represented tree where app depends on the SCons script, depends on the app program, which depends on the object file, which depends on the source file, which depends on the header file, and the compiler. So you'll notice there's a lot of files here we didn't list in our SCons struct or SCon scripts. That's because one of the things SCons will do is find what's called implicit dependencies. So dependencies you haven't listed. And those are found by scanning the files and by looking at the command line. So in the case of the header file, app.c has a pound include. Well, SCons will process that file and find all the includes and find them in the CPP path and add them to the dependency tree. So in the case where you have a C file that includes a header file, which is generated, and another rule that generates that header file, it will now know that that other step that generates the header file has to happen before you compile the source file. All right, so now we run the two programs. We can see that vanilla is actually vanilla and chocolate is indeed chocolate. So this is sort of the 10,000-foot view. What happens when you run SCons? SCons will do some initialization, then it will load the SConstruct you specified. By default, it's named SConstruct, but you can specify alternate files on the command line. And to make Jeff happy, all of our command line options are very short. They're generally single letters. So there's many of them. And to build parallel is just -J and a number, or -J is unlimited. By default, the builds are single core. Okay. Now, once all the SCon scripts and SConstructs have been loaded, SCons will process all these targets and sources and build a directed asymmetric graph, which contains all the targets and sources. And it will also scan all the source files to add in those implicit dependencies, which may indeed actually connect builders' targets to sources for other builders. Once that tree is built, it will say, look through the tree, try and find a target which is ready to be built and build that. Once that's built, it will mark any targets that it has that it's going to generate as built. And so the next pass through that tree, it will see potentially more targets which are ready to be built, and it'll repeat that until it's done. And then when it's completed, it writes out a database of all the targets and sources, all their dependencies, and the MD5 hash of all the dependencies, and the MD5 hash of the command line used to build those targets. And that is the quick intro to SCons. So we can take some questions. Oh, and these examples actually are in a GitHub repo if you wanted to look through them later.
Bill, do you want us to read the questions, or do you want to look at the Q&A part?
I'll look at the Q&A. So David asks, would this replace my CMake build system? Would it be worth porting it? Under what situations? So if anybody, well, build systems can be kind of a religious subject. Some people love one or the other because either they know it or they have run into problems with other ones. CMake has a lot of good things. It has support for lots of builders, and lots of products distribute information to help build them their generated packages and to glue packages together. It can generate MSVC, it can generate Ninja files, it can generate make files. But debugging CMake and getting it correct is pretty darn difficult. As I've shown before, let me bring up a simple slide here. Okay. All these files are plain Python. And actually all builders, of which in this case program is a builder, returns a list of nodes, which are the targets generated by that. You can actually break into a debugger and inspect all kinds of information about the targets. You can stick print statements in here. You could put for loops. I personally think doing a complicated build in CMake and getting it correct, and by correct, I don't mean just working. I mean, incremental builds are always correct. It's much more difficult. So, you know, in general, I know SCons very well, so I would always suggest SCons in most cases. There's a few cases which wouldn't make sense. If you had an electric cloud cluster, SCons doesn't spit out make files that could be run by it. But yes, I would say on almost any situation you could replace CMake build system with SCons. Would it be worth porting it? It really depends on what is your pain point with your CMake at that point in time. I mean, if your CMake build system is already working and you're happy with it, then then it becomes like a religious debate about which one is better. But if you're stuck and you can't get it to work, then it's worth looking, in my mind, it's worth looking at SCons. Okay. Dave says, so the list of programming language for which SCons has built-in support is not a definitive, complete list. These just seem like the most popular compiled languages, which users might be familiar with and might have build systems that currently build. You can package Python and you can bytecode Python using SCons. In fact, one of the Python packaging developers actually created SCons extension, which builds packages builds wheels for uploading to PyPy. So I'm not sure if that really answers your question, but built-in support really means, does it have support for building, compiling targets built with that compiler? And Python is one of those, but it's just not listed. Let's see. David asks, is there, SCons can get quite complex. Is there a linter on top of AutoPep, which can help us clean up the files with best practices? Currently, there isn't. In a lot of cases, to determine whether you're doing something not quite right in your constructs, you probably need more context than AutoPep would have. In fact, it's actually good timing. We were talking about this amongst the developers that some kind of a lint mode would actually be a good idea, because it would be fairly easy from watching the way people call builders and do other things within S constructs to catch some easy to fix bad practices. Oh, Sean Browers is online. Let's see. Good point, John. Yes, my bad. So my first slides I've ever made for a presentation, so auto-corrected incorrectly. Let's see. Monty's asking if you're building a large, really big project with a lot of SCons script files that rarely changes, a way to avoid rereading all the. I mean, in general, reading the SCons scripts is pretty darn fast. The things that are somewhat slow are reading the previous build's database, writing the database at the end. The biggest time sink in the build is actually expanding out the command lines. So that's probably about 50% of a what we call a null build, where no files are actually compiled. It's just being checked to see whether it needs to recompile. So I think in most cases it's not really that useful. It won't really help you speed up all that much. You could do things like watching for specified command line targets and only processing SCon scripts that are directly related to those. But we're actually, I mean, we're aware of there are some performance issues, and those have been actively worked on for many years. MongoDB has actually supported a lot of those efforts, does some of those internally. And we are actually getting ready to beta a Ninja output mode. So that would be significantly faster when that's completed. That was contributed by MongoDB, which is not as entirely general at this point, but if you had a plain C, C++ build, it probably would work pretty well. And I think that answers that question.
Yeah, there were a couple of other questions in normal chat that they didn't put them here in the Q&A. Tracy Carver asked, is this a suitable replacement for NewMake? Why or why not? Pros and cons.
Let me see.
It was pretty far up there.
Oh, yes. I mean, that's what it was created to be. So there was a paper written in 1998. Let me take a look, see if I have it here. Which inspired more than just SCons to take on replacing. See if I can share that other screen. Okay. So this paper came out in 1998, recursive make considered harmful. And it talked about the situation. I mean, the common practice at that point in time was that each source directory would have its own makefile, which was standalone, and parent directories would call into those subdirectory makefiles and run them standalone. So the context of the context of your entire build would never be captured by a single makefile. And also, I mean, have you ever tried to debug GNU Make for anything more than simple builds? It really gets very painful. And you don't have any looping constructs. You can't put prints in there. If you do a make-p to get a dump from make, you can certainly figure everything out, but having Python as your scripting to build your build system actually makes things go a lot faster. Having built-in scanners for various languages adds all the implicit dependencies, so you don't have to run make depend. Being able to create builders that do all kinds of interesting things, like you can write Python functions that generate your command lines on the fly based on source file names or the number of source files or various variables you specified to the environment you're in. There's just a lot more flexibility, debuggability, and also makes only timestamp based. So if your file changes and the timestamp doesn't change, you'll miss that change entirely. So I would say yes. I mean, I wouldn't use make today for anything but something really trivial. Is there any other questions that I missed?
I think that's it.
Hey, this is Jeff. I got a question.
Sure.
You were mentioning MongoDB. Is there any other famous users of SCons?
So VMware.
Okay.
They actually supported the project early on and hired Steven to do some consulting and add some features. They were very active in the community for a while, and then they weren't for a while, and they seem to be re-engaging now. But all along, it sounds like they've continued to use SCons and actually have a lot of internally developed bug fixes, feature additions. We work with anybody who wants to contribute features back to the project. Oh, Dave
Cool.
has a question. Oh, does that answer your question?
Yeah, yeah. I was just curious.
Oh, there's actually 2 or 3 embedded software platforms. So one called Platform.io, one called IoTivity, that are built on top of SCons. So SCons is really a toolkit. You can build anything you want on top of it. It's MIT licensed, so you can package it and use it in a commercial product if you want. We do prefer people contribute back to the project, but it's not a legal requirement. The license doesn't require it. But generally, it's in people's best interest to contribute back. And it is interesting to continue managing and supporting and developing a project that's almost 20 years old. We recently purged, I think, almost the last bit of our code, which supported Python 1.5.2.
Wow.
So we have a bunch of to-dos that say now when we drop Python 3.5, we can get rid of this. That's another challenge with this project. But it has been around 20 years and it's in pretty broad use. So it may not be the fastest project out there, but it's much easier to build your software correctly. So the question is, do you want to lose, I don't know, 10 or 15 seconds per build, or do you want to lose 4 days because your build didn't do things right? Usually when you're releasing the product or when you release it and your customer has it and reports a problem that you then realize actually was because your build was not right. So, and we are actively working on trying to get rid of that cost penalty for correctness.
I think there was one more question. Do you use multiple cores to compile things in parallel, like Snakemake?
Yes. Yeah. So since day one, SCons has supported parallel builds. -J and number of cores will do it. We are looking into ways to allow specific builders to limit parallelism. If you're doing a huge build, the link step can often be very memory intensive. And being able to say, I only want 3 link steps, but I want 64 compile steps to be allowed to happen at once could be useful. And I think that's all we have, right? All time we have for tonight.